Hello, good day. I want to quickly talk on this topic, Newton's laws of motion. So it's the next topic that we're supposed to discuss. So Newton's laws of motion. I will try to make this as easy to understand as possible. Okay. So Newton's laws of motion. I know it's not new. It's not new to us. We know that there are three Newton's laws. Okay, so let's first of all, before we go over that, before we get to that, let's look at how force and interactions. So what do we mean? We know that there are, since we're dealing with this for Newton's laws of motion, we'll be looking at forces that we can forces called contact forces. Okay, contact forces. Majorly, those are the forces that we're going to be treating under this topic. So we know that there are frictional forces, which is an example of a contact force. We also know that there is normal reaction forces, and we also understand that there are tension. There's what we call tension force. Tension force is the force that we experience when we pull on strings or when we carry something heavy in a bag. Okay, the force that we experience when we pull a string or carry a bag or carry a nylon bag that has something heavy in it, that force that pulls on our fingers is called the tension force. Friction force is a force that opposes motion. Normal reaction force is the force that is usually equal. Okay, it acts opposite to a body. Okay, it's usually equal and opposite to the weight of a body. Okay, so for example, when you have, according to, if you look on the screen, this 4.2 figure, 4.2 that we have here, four common types of forces: the normal force, which is when an object rests or pushes on a surface. The surface exerts a push on it that is directed perpendicular to the surface. So yeah, that's why I call it a normal reaction force. Normal meaning that it is perpendicular. It acts perpendicular to the surface it acts on. And it's usually opposite and equal to the body. Okay. So these are examples of contact forces. Weight is also an example. Weight is also an example of a contact force, and it's we can define it as the pull of gravity on an object. Okay. That's the amount of pull that gravity, the Earth's gravitational field has on an object. So we also understand we've done forces and how to calculate the resultant force. Okay. The resultant force is like, I explained that it's the force that will have the same effect as the net. I mean, it's the resultant force is a force that will have the same effect as several forces acting on an object. So it's like, say, if we have an object that is acted upon by two forces, let's say two forces, okay? And if those forces were removed, a resultant force is a force that will have the same effect that those forces would have had on that object if they were left to act on the object. I don't know if we understand. For example, let's look at these picture here, superposition of forces. Let me go over this first. So superposition of forces. I'll quickly read through this So just follow me. When you throw a ball, there are at least two forces acting on the ball. So there is the force you throw the ball with from your hand, and there is also gravity. Gravity will also act on the ball to pull it down, and then the force with which you threw the ball out of your hand. So these are at least these two forces will act on it. Now, the effect, these two forces will have these, when these two forces act at the same time on the body, these two forces will act at the same time and at the same point on the body. Now, the effect on the body's motion will be the same as if a single force called a resultant force were to act on that ball as well. So, like if we could combine the two forces together and replace with another force, then that will be the resultant of those two separate forces. Okay, so R being the single force can be calculated by calculating the vector sum of the two forces, F1 and F2. So if we are able to do that, the resultant force we get is going to be is a single force that will be equal to the vector sum of those two forces. So this is what we know as the principle of superposition of forces. Okay, so again, I repeat it. A resultant force is that single force that will have the same effect as several forces acting on an object at the same time. Okay, so it's like saying if three little children were pulling on a tire, and then maybe someone then a grown-up asks them to leave it alone, like asks them to stop pulling, and then he decides to pull for those children. So it's like I'm using that to explain what a resultant force means. So that single adult is like the resultant of the three children who were pulling on the tire initially. Okay, so now this is important to our topic, Newton's laws of motion. That's why I'm explaining that first. So here we, in this diagram, 4.5, looking at these two diagrams, we can see that the force F, which acts at an angle theta from the x-axis, may be replaced by its rectangular component vectors f of x and f of y. So like this single vector f here in the center is the resultant vector of these two components. So we can say like these are the components of the single vector. Okay, so these are the components of the single vector. So if the single vector were added in vector form, if we found the vector sum of these two vectors, fy and f of x, then we'll get f. Okay, so component vectors fx and fy. Now, resolving this vector f into its component, we have to we use trigonometry, and we know that resolving a vector in the x direction, the horizontal direction, we're going to have it as f cos x, and resolving this vector in its in the vertical direction, which is f of y, will give us f sine theta, which is this f sine theta. Okay, so to go on, we can also just give me a moment. Okay. So we can also see that When we have several vectors, like I said, we can always find the vector sum to get the resultant. So this is important for our topic, as I'm saying. And then, as I was saying, and you would often come across this Greek letter called sigma. It represents the addition of several forces. So we would refer to it as the net force, okay? Net force for several forces, when we have several forces acting on an object, okay? So we read sigma F as vector sum of forces or the net force. Okay, so if we have several forces acting in the horizontal direction, which is R of X, then we can calculate this vector sum of those forces in the horizontal direction. And if we have several forces acting in the vertical direction as well, then we can also calculate the vector sum of those forces in the vertical direction before then calculating the resultant of those two forces. Just to further elaborate on what I mean, say there are several forces acting like that, in the same vertical direction. We have F, Y, and so on, Fy. And then we have several horizontal forces also acting. Sorry for my drawing. It might not look straight, but because I'm using my free hand. So we have F of X, Fx, and then F of X as well. So if we were to calculate the resultant of these forces, we would first need to calculate the vector sum of the forces in the y direction, which should give us the ry, okay? And then calculate the vector sum of the forces in the x direction, which will give us our rx. Now, after doing this, we have to do this first before we then go on to calculate. Now that we have resolved all these vectors in the vertical direction into one, which is our ry, and resolving these forces as well in the horizontal direction into one resultant, which is our rx, we can then find a vector sum of these two, okay, which will be the vector sum of these two will then be, sorry, hold on. So R, Y, R, X will then give us the vector sum R, okay? So this will be something like that. That was R, which is the vector sum of R, Y, and then R, X. Sorry, I omitted something, squares. So I hope this is understood. So we can go on. So as we go on, it's also possible to calculate a vector sum or finding the resultant of several vectors acting in a three-dimension plane. Okay, so if we have a situation where the vectors act in a three-dimension plane, x, y, z, like I've explained to you before in class as well, x, y, z plane, then we just need to calculate all those vectors in their respective directions and then calculate the resultant of all those vectors. So this will be how to do it, okay? So all the vectors resolved in the horizontal direction, the vectors in the vertical direction also resolved into one, and then the vectors in the z direction or the z direction resolved into one, and then all this added using the vector addition. to get the single vector that can replace all those vectors. So I hope this is clear to you. Now, let's look at an example. Superposition of forces. We have an example on the screen. 3 professional wrestlers are fighting over a champion's belt. Okay, this is the figure showing it. 3 professional wrestlers are fighting over a champion's belt. Figure 4.8a shows the horizontal force each wrestler applies to the belt as viewed from above. Okay, the forces have magnitudes. F1 is 250 Newton, F2 is 50 Newton, and F3 is 120 Newton. Find the X and Y components of the net force on the belt and find its magnitude and its direction. So we're to find the X and Y components of the net force on the belt. Now, we can see that from the question, three people are struggling with a belt. Okay, maybe they are wrestling with it, they are fighting for it amongst each other. So 3 people are pulling on the belt. So it's like maybe this is the belt, someone is pulling like that, the other person is pulling like that. So this is one. Okay, these are the people. These are the direction of the forces. F2, 1, F3, F2, and F1. Okay, so we're to resolve these forces in the X direction first, and then the Y direction. We're to resolve these forces first in the X direction, and then second in the Y direction. So let's look at the solution together. So from this, from the question, F1 is 250, F2 is 50, F3 is 120. Okay, so we can see that okay. So as I was saying, we need to solve this question, example 4.1. Now the 3 forces that we need to resolve from the wrestlers, these are the 3 forces, F1, F2, and F3. So basically we have this, something like this. No, let me try to do a clearer drawing. So we have something like this, one force acting like that, and then there is another wrestler pulling this way, and then there's a third wrestler pulling down. So these are the forces from the wrestlers. So this is our F1, F2, and our F3. All right, so we're starting or taking our reference point, our starting point from here, which is our X, which coincides with the X direction, and our vertical direction, which will be our Y direction. Okay, so like I said, we need to resolve all these 3 forces in the vertical component or vertical direction, as well as their horizontal direction, because there are single forces that will have both, that should have both horizontal and vertical components. So we want to resolve them. So they're like single resultant forces that we want to resolve into their X and Y components. So to do the first one, I said we're taking this as our reference point. So according to the question or from the drawing, we can see that the angle that F1 makes with the horizontal, they've given that to us, the angle it makes with the horizontal is 53 degrees, okay? So it's like they're taking it from here, this line. But I want us to work from this direction, the right hand. So all directions to the right will be taken as positive, and directions to the left in the horizontal I will be taken as negative, while directions above the line will be taken as positive and below the line will be taken as negative. Okay, so from here, right, if this space is 53, then it means from here to here will just be 180 minus 53 to get this 127, which has been done here. So it means the angle between F1 and the horizontal, the angle which the first vector or the first force, I mean, makes with the horizontal is 127 degrees. Now remember that when you want to resolve a vector in the horizontal direction, then you're going to use that vector F cos theta. And if we are resolving into the vertical direction, then we're going to use the sign F sine X or theta, whatever connotation you want to use. So it could be theta, it could be X. Just know that we're referring to the angle, okay? Do not be confused. So our force, starting with the first force, which is the vector here, we'll resolve it into its vertical and horizontal components. So that's what has been done here. This is the force, the first force, 250, cos 127, which is the angle it makes with the horizontal line. So doing that gave minus 150 Newton. And that's why, the reason why it's negative, as you can see, it lies on the left-hand side. Okay, so which means this is right because it lies on the left side. And I told you earlier that we're taking directions to the left as negative. Vectors that fall or that face the left direction, okay, are taken as negative. Then for the horizontal component, that's been F sine theta, which is 200. Now, for the second vector, as you can see, it already coincides with the x-axis. So it lies on top of it. It coincides with it, which means the angle between that force and the horizontal axis is 0. There's no angle. So that's why theta is going to be our 0, or our x is 0. So it means for the second vector F2 in the horizontal direction is going to be F, which is 50, cos 0. Also in the y direction is going to be F sine 0. Okay? And for F3, the third vector, as you can see, it's downwards, it's vertically downwards, okay? So it's going to make an angle of, remember, this is our reference point, okay? So we're going this way. Starting from here, getting here is going to be 90, okay? It's 90, but because we surpassed it from here to here was 127. Now, if you keep going, this is what, if you get here, this is 180. And then if you keep going, 180, this is another 90 degree. So 180 plus 90 gives us 270 degrees, okay? So which is the angle that F3 makes with the horizontal. Please do not look at it from this direction. We're taking this as our reference start point so that there will be no confusion. all directions are taken with respect to this point. This from here, that's the direction we're going, okay? So it's 270. It makes an angle of 270 with this x axis, I mean. So 70 will be the angle that we use. So it means F3 in the x direction will be F cos 270, F is 120, and in the y direction is F sine 120. So as you can also see, in the y direction, the vertical direction, it's negative, and in the x direction is 0 because it has no components in the x direction. It acts downwards, okay? So, and because it acts downwards, I told you again, just to remind you, that directions below the axis will be taken as negative. Directions above the axis will be taken as positive. So because it comes below, that's why it's a negative, which means we are correct. Which means the calculation is correct. So now the next thing to do, since we've resolved the three vectors in their vertical and horizontal directions, all we need to do is then add them together since they are now in the same directions. So in the x directions, these are the forces, minus 150. So we have this, and we have this, and we have this. So they are all added together as is, minus 150 plus 50 plus 0. And in the y direction as well, they're all picked and added together. So we have this. Now, this in the x direction is negative. Now, as you can probably tell, it means this vector is going to face, or is going to be in the left direction, okay? While this, since it's positive, is going to look like this, okay? So this is what we are going to have, Rx and then Ry, which is what we have here, okay? Ry, Rx. So we can then add this using this equation. So using this equation, we can then say R is equal to Rx squared plus Ry squared, which we would see in the next page. Let me quickly scroll down. Sorry. Okay. So that is it in the next time. So which is what I just said. It's been solved now for us. The negative 100 squared plus 80 squared. And we have the answer. So this is the resultant vector, 128. Now, what angle? We know that the resultant vector is 128. So what direction? So, because we found the magnitude, 128. Now, what direction is it acting? To calculate direction, we use this tan. You know, remember from your trig, tan opposite over adjacent, okay? You can use that to remember. So if I scroll back up to the question, so you can see, to the diagram, I mean. So we can see that here, opposite, using this is our opposite, Ry, and the adjacent is Rx. But usually, anyway, it's usually Ry over Rx, okay? Like the vertical over the horizontal. Vertical over the horizontal. So you can also use that to remember. So since it's vertical over horizontal, then that's Ry over divided by Rx. So that has been done. And that's, do not mind this arctan, it's just a way of writing tan inverse, okay? Tan inverse of Ry over Rx. So the which is 80 over minus 100. And solving that, we have the answer minus 31. Now, this minus 31 just tells you that, like, this is what they mean. This is what it means. So this is the Rx, which was 100. And this is our Ry, which was 80 Newton. Remember, I told you this minus 100 here tells us that it lies in the left hand side, the left direction. It's pointing towards the left direction. So, which also means that this minus 39 is telling you're taking the direction of the angle with respect to this point starting from the left. Okay, remember we took our direction from the right, okay, and we went like that. But here minus 39 just means that they're starting from here, the left, and going somewhere in between. Okay, so this will be 39 degrees, somewhere around like that. 39 degrees, okay, which is our R. Now, if they were to take it from here, then it means we'll do 180 minus 39, which will give us 141. So 141, the answer is 141 if you're going from this direction, from the right hand side. But from the left hand side, the direction is 39 degrees. I hope we understand this explanation of this question, okay? If you do not, please, you can watch over and over again so that until you get a very clear understanding. And any question you have, please just leave in comments for me. Leave in the comments. I'll go through it and explain further, okay? So let's go on with some things before I round up on this video. So because I do not want it to be a very long video so that it doesn't become too tiring or boring to understand. Okay, now to test your understanding of what we just did. Figure 4.6 shows a force acting on a crate. Let's see, where's 4.6? Can we say 4.6 here? Okay, I'm trying to look for a figure 4.6. Okay, so this is the figure I think they're talking about. So this is a man who is pulling this box. So I think this is the crate they're talking about. So I want us to keep this diagram in mind. This is a man pulling on a crate or a box. So the question says, or the evaluation says, so my computer decides to hang, freeze.